So today we'll talk about the flow systems in tall buildings first. So whatever the structural form that we use, we need to have a flow at each level, and the simplest form of a flow is the normal solid slab, and solid slab can be one way or two way. And then it is also possible to have the simplest possible is solid slab, and then we can also, the simplest possible is solid slab one way spanning. Then we can think of solid slab two way spanning. And when you have two way spanning, the loads are transferred in both directions, so it's structurally more efficient. The reason is, even in a one way slab, you have to provide crack controlling reinforcement in the other direction. But we are not making use of that reinforcement for structural carrying capacity. So because of that, one way slabs are not very efficient, but two way slabs are more efficient. And in tall buildings, again, another aspect that we have to look for is the number of columns or the number of column free spaces, and the span of the column free spaces. So in a tall building, because we are transferring large loads, we have to make sure the foundations can be independent. Otherwise, what happens is, if the foundations are too close, then you will find that all these foundations are overlapping each other. So to prevent that happening, generally we go for spans like 6 to 7 meters as a minimum in tall buildings. But actually, sometimes you can use something like 7.5 meters and even up to 9 meters in a tall building. So when we talk about that type of spans, sometimes, let's say you are having 7.5 meter by 7.5 meter span, and you want to use a two-way spanning slab, and the minimum slab thickness might come closer to 200 millimeters. Now you can see 200 millimeter thick slab is a fairly heavy slab. So one of the options you have is to consider having secondary beams. So if the span of the beams are in the range of 7.5 meters, then you can think of having this secondary beams. So basically, when you have something like this, having something like 7.5 meter spans, then you can actually go with secondary beams. So these are secondary beams. Can you see it?
Yes,
Yes. All right. Good. And then generally these secondary beams are detailed in such a way that we make them pin-ended. We make them pin-ended at the main beams. These are the main beams. The reason for this is that if you do not make it pin-ended, then you will be transferring a torsional moment onto the main beam when you load this side fully, and when you have no load on this side, then the moment on this side will be more, moment on this side will be less. So what happens is, there will be a torsional moment. And we know that, beams are not very good in carrying torsion. So because of that reason, what we do is we'll do the detailing with nominal reinforcement at the top. Nominal reinforcement or nominal or crack controlling reinforcement. We'll have nominal reinforcement or crack controlling reinforcement only, and we'll analyze the secondary beam as simply supported. But the other important point is, when you have the secondary beam meeting the primary beam, now we are transferring a fairly high load onto the main beam. So we have to have a lot of links here to ensure that this beam will not crack and fall. So you have to have a lot of links here, which is sufficient to transfer all this load. Say if we are transfer it back in this direction, so that this load is now suspended from the top of the beam, top of the main beam. So this is the main beam. This is the main beam. And we have to make sure the load that is carried by the secondary beam is transferred to the primary beam at the top level. And we can't just do it. So what we do is we will provide a lot of links, closely spaced links in this area. And this, the area of these links should be sufficient to transfer the load to the top level. So basically you will hang the links from the top bars, so that this beam will not be able to crack the concrete and fall. So when you have secondary beams, you have to be a little careful, and you have to provide some extra reinforcement in the main beam in the form of links to ensure that the secondary beam is firmly kept in position. So that's one of the requirements. So I'll share the screen again. So when the spans exceed 6 to 7 meters, the possibility of using secondary beams could be given some consideration. So what are the advantages you will gain by having this secondary beams? And the advantage you can gain by having the secondary beam is, without the secondary beams, with this type of span, 7.5 meter spans, you will find that the slab thickness may be about 200 millimeters. Whereas, the moment you have secondary beams, you can reduce the slab thickness to about 125 millimeters. And if you look at the density of or the weight of this slab, the weight of this slab is 0.2 multiplied by 25, and the weight of this slab is 0.125 multiplied by 25. So the weight of this slab is 5 kilonewtons per meter squared, whereas the weight of the other slab is 0.125 multiplied by 25. So that is 3.125 kilonewtons per meter squared. So you can see we are saving about 1.875 kilonewtons per meter squared weight in every square meter. And if you are considering something like a 30 to 40 story building, then you can see the saving can become very significant. So this amount will be saved at each floor level. So because of that reason, you have to spend a little time and select a suitable slab system, so that the slab system is fairly optimized in the structure. So I'll share the screen now. So in addition to that, this is the basic system where we have beams and slabs. We can also have flat slabs or two-way spanning slabs. And in the case of flat slabs, we can again have two variations. And one is, we can have a flat slab with drop panels. So that means, close to the column, we can have an arrangement like this, or else we can also have drop panel and a column head. But both these have a disadvantage, and that is, during the casting, you have to form all these shapes. So because of that reason, structurally this may not be very efficient. When it comes to construction wise, it may not be efficient. But when it comes to the structural behavior, this is reasonably good because we can prevent punching shear possibility by increasing the thickness of the slab. So this is the flat slab with drop panels. So these are drop panels, and this also has drop panels, but it also has a column head. Also has a column head. So these are some variations, but what we prefer for a large building is just the slab or a plate or a slab with no drop panels, no column heads, and that is the preferred shape. But the problem is the thickness of this slab can become something like 200 millimeters, and if the slab thickness is more than 200 millimeters, you can even provide some shear links around the column perimeter to prevent shear failures. That is possible, but not very easy to provide it in practice at site conditions, but you can have some links also. So in addition to that, you can also consider having a situation like this where we run pre-stressed tendons like this, and by having pre-stress we can lift the slab up and transfer some of these loads onto the column region. So this will be even more efficient, and these days this is gaining popularity due to the need for less reinforcement, because most of these loads are now transferred onto the column strips. So because of that reason, you'll find that the almost 80 to 90% of the self weight of the slab can be transferred onto the columns. So with that, you get a better and more efficient system. So in large buildings, pre-stressed concrete is also becoming popular. Pre-stressed concrete is also becoming popular. So those are the different variations that you can have with slabs. This is the pre-stressed concrete system, and in the pre-stressed concrete systems, generally what happens is when you have columns, you can have the tendons running this way and transferring all the loads in this area onto this one. So you will need a lot of tendons this way. So because all these loads are now transferred onto the strips along the column lines. So basically you'll find these are carrying heavy loads, so you have to have a lot of tendons. So most of the flat slab pre-stressed concrete slabs are designed with this type of system where you will provide pre-stressing in one direction with parabolic cables, so that the force in the middle of the structure, middle part, can be transferred onto the column strips. And in the column strips, you will have a concentration of pre-stressing, so that all these loads can be transferred onto the columns. All these loads can be transferred onto the columns. So these are different variations that you can have with respect to slabs. So I'll share the screen again. So they could be this pre-stressed concrete these flat slabs can be out of reinforced concrete or could be pre-stressed. And when you pre-stress it, you can actually reduce the quantity of reinforcement significantly. And in addition to that, if you want, you can actually use these steel decking systems where you have the steel deck supported on the steel beams, and then you'll need only a thin concrete where even the steel deck can be considered to act as a reinforcement. So that is a good system where you get steel beams and the decking sheets having a certain shape, and on the decking sheet you will have something like a thin concrete, and the concrete will behave structurally as a composite material with the decking sheets. So for any span, you need to have a reasonable depth. So you'll find that the decking sheet is profiled in such a way that you will get some kind of ribs. And I can again show you the shape. So basically, you will have a system where you have the steel beam, and there will be a shear stud, and then you have another beam, and in this direction, the flow system will be done. And although I draw it with a certain thickness like 150 millimeter, the actual, if you take a cross section, this will look like this. So there will be, for better bonding, there will be shapes like this, and also to stiffen the shape. And then you lay a thin concrete, something like 60 to 75 millimeter, and this can form the concrete floor. And because the steel deck has some strength, you need only few props underneath it, not a full shuttering, but few props to make sure that the steel deck does not deform too much. The steel deck can actually act as a formwork, and it can actually become a composite material combined with the deck concrete. In addition to that, this decking can act as a formwork during the construction. And because of this particular shape, you'll find that the deflection of this system can be controlled very effectively. The reason is it's lightweight, but it is having ribs. So we can actually have this type of systems as well. So you can have so many different types of systems in a building to act like the slab. And then we will also look at, what are the load combinations that we have to consider in the design of these tall buildings. And if you look at the load combinations, in Eurocode, for dead loads, to relate it to the ultimate loads, we use a factor of 1.35. And for live loads, we use a factor of 1.5. So when you want to design a beam, what we do is we'll go for 1.35 GK plus 1.5 QK. We'll use something like this. That means all the spans are loaded. And in addition to that, we'll use a subframe like this. So we load all this. And then we'll also go think of having some pattern loading. I'll come to that in a moment. But in a tall building, the situation is a little different because we have heavy wind loads also acting. So you have to consider the combination of wind and imposed. So we have to think of how to combine them. And that's what you can see in this table. So for live loads in the Euro codes, you can have variable action. And under the variable action, also you have one called leading variable action. And the other variable actions will become accompanying variable actions. So when you are looking at a load combination where you want to combine the bin load, say WK, with GK and QK. So when you have WK, you have to combine it with GK and QK. We have to consider the different load combinations that can be possible. And in Eurocode, you have variable action, and under that leading another. So in this one, all these we use a factor of 1.5 for variable loads. But what happens is, this one, the leading action we multiply by 1. For the other action, we multiply it by 0.7 or 0.5. Now, what is the reason for this type of, considering this type of combinations? And we'll come to that in a moment. So what happens is, we want to find the most critical combination. One combination that is possible is you will consider only the dead and imposed loads, but you will ignore the wind loads. So that is the first condition, 1.35 and 1.5. In the second combination, we have the dead load acting on the structure, and also we have wind load acting on the structure. That means, immediately after construction, you will find that, this the structure is not yet opened. So that means still, doing the finishing work. But most of the loads, say 95 to 98% of the loads that you have anticipated are now acting on the structure with respect to the permanent loads. So there can be a little room for adding few more loads, like the finishers, the weight of finishers and so on, that are going to come in the last part of the building construction. But building is now almost there, no imposed load, and you can have a cyclone on a day like that. To take account of that, you have the dead and wind case, where wind is the leading variable. But when you are combining dead, imposed and wind, you have to select which one is leading. The moment you select one leading, the other one become the other one becomes under the other category, where you do not have to consider the full load. So basically, if you consider imposed load as the leading, then you have dead 1.35, imposed 1.5. For the wind, we use only 50% of the wind. On the other hand, we can also have a possibility. The building is not carrying full live load, as you can see here. So building is carrying only 70% of the live load, and a cyclone hits the building on that particular day. So we have to consider dead load, imposed load, and wind load, all three. Then you can ask the question, why are we multiplying by this 0.5 and 0.7? Here we have multiplied for wind, we use this factor as 0.5, whereas for imposed loads, we use a factor of 0.7. So what is the reason for considering all these different values in when you are combining the loads? What is the reason for all these different values? The reason is, in a tall building, there is no chance for all the loads to act simultaneously at the maximum value. So what we do is, we assess the values based on probability. So when you assess the values based on probability, you'll find that, when the building is fully loaded, the chances of cyclone hitting can be less. So the impact of cyclone we consider it as 75% of the maximum value. On the other hand, when the cyclone is hit, there is a chance that the building is not fully loaded under the imposed or not fully loaded with the imposed loads. So that's the other possibility that can occur. So we have to consider all these different possibilities, and that is all based on the probability that all the maximum loads cannot act simultaneously. So that's the basis. And then in the case of designing the beams, we have to consider pattern loading. When you are considering the pattern loading, the ideal way to consider the pattern loading is you go with this span, load it with the maximum. You have minimum load on this span, maximum load on this span. So basically, if you are having the maximum dead load here, 1.35 GK, and if you want to get the maximum out of balance moment, don't have any load on this slab. And then only you will get the maximum moment here, maximum out of balance moment. And that can be used to calculate the maximum load coming onto the columns. So in addition to that, we can also see that with the minimum load here, the maximum bending moment will occur in this particular span and also in this particular span. Then you will ask why Eurocode specifies 1.35. The earlier British code we used to have the value of 1.0 GK, but when you look at Eurocode, it clearly states, that this type of massive variations are not generally possible. So if you are considering the maximum dead load for one span, make sure you are considering the same maximum on every flow, every span. On the other hand, if you are going with 1.0 GK, make sure this is also 1.0 GK, this is also 1.0. So because of that reason, when you do pattern loading, generally we like to use the maximum load, and what we do is we use 1.35 GK plus 1.5 QK. But here in the next span, we use 1.35 GK plus 0 QK. So this is how we create pattern loading in to get the maximum bending moment. And then you'll ask why we are having these extra frames analyzed. Can't we get the bending moments and shear forces on beams directly from the 3D model that you would make for the structure? Again, the answer is, if you look at all the codes, it can be the Euro code or British code or Australian code, for beams, they always recommend considering the pattern loading. And the idea of pattern loading is we load one panel with the maximum load, and then we'll have lesser loads on the other panel. So finally, we can end up with the maximum moment on the beam. So then we can also have a look at one of the common elements that we get in tall buildings, and that is the shear wall. And in the case of shear wall, if you look at one side, if in the wind is acting, what happens in the shear wall is something like this. So we have the shear wall. The shear wall like this. And it's carrying vertical load. It's also carrying the lateral load. It's carrying the vertical load and the lateral load. So the vertical load can be due to GK and QK. So due to GK, you get a stress diagram like this. This is uniformly loaded. So this is due to GK effect. Plus QK also you get an effect like this. Plus due to wind load, you can get an effect like this. This is due to WK. So when you combine these two, you can get a situation like this, or a situation like this. So when you combine all this, you might end up with a situation like this. And generally we prefer a situation like this, because here the wall is cracked. So how do you ensure that we get this situation? So whenever you have a shear wall, you might have a situation like this. So this is the lift core. So here you get the lift lobby. So on this side you get other slabs. So if you are having all these other slabs that are transferring the load onto this, and finally to all the main elements, then you will find we can increase the value of GK, and also we can increase the value of QK. But because we are having voids on this side, you will find that the load coming from this side is not high. So if you want to make sure we do not get this type, we have to make sure these loads, the vertical load transferred onto the shear wall, are high enough. On the other hand, what you have to do is this WK induced bending moment can be shared between a number of walls. So instead of having one wall, if you're having 3 walls, then each wall will be carrying a lesser moment. The moment carried by each wall will be m by 3. So there are 2 options available. One option is, have a greater number of shear walls. The other option is ensure that you are transferring adequate load onto the shear wall. And if you have a situation like this, where you have another opening on the other side also, that may not be very attractive, because this particular shear wall will not have enough vertical loads to suppress the stresses caused by the bending moment. So it's very important, when you have shear walls, adequate load is ensured onto the shear wall so that it will behave in compression like this, rather than like this. So we don't like this situation where the wall can become cracked. So to generate the worst case, then we have to see the different load combinations we have to consider. But here you get compression maximum. Here you get compression minimum. But on this side, you might get tension as well. Minimum compression can be tension. So what is the load case that you have to consider to get this tension effect? To get the tension effect, if you consider 1.0 GK and the maximum load WK, that is 1.5 times WK, then the axial stress will be minimum, the bending stress will be maximum, and once you add these two, you have there's a chance of getting this particular stress distribution. So we actually want to see whether this occurs. So what we do is we apply the maximum wind load on this side and the minimum vertical load, and this is applicable only to the tension side but not applicable to the compression side. For the compression side, we have to make sure we get 1.35 GK and the maximum load 1.5 WK. So this is how you have to look at it, and this will give the compression. So if we summarize all the load combinations that we have to consider, the first case is 1.35 GK plus 1.5 QK. So that is the vertical load case. Then you can get the live leading case, 1.35 GK plus 1.5 QK plus 0.75 WK. And then we can also get wind leading case, 1.5 into 0.7 times QK. 7.5. Sorry, this 1.5 times WK. So you can get this. And in addition to that, so this will give the maximum case. And in addition to that, we also have to consider this particular case where you get 1.0 GK plus 1.5 WK. So we have to consider that case. And we do not have to consider a case like 1.35 GK plus, sorry, we can consider this case also, but there's a chance that this might be more critical than this one. So this might be more critical than this one. So if that is the case, you know, no need to consider this, but it's very useful to consider this particular load combination. So basically, when you are dealing with a tall building, you have to consider all these different possibilities. And in Eurocode, all these different combinations are given. So you can see on the compression side, the worst case can be due to one of these two. And in the tension side, the worst case will happen when the wind is maximum and the vertical load is minimum. So these are different load combinations that you have to consider when you are finding when you do a 3D model. So those are the basic things I wanted to cover before we move on to the real applications. So before we go into the detailed applications and the modeling and wind calculations and all that, there's a general presentation that I have made on tall buildings that will give you an overall idea about the design methods. So after the lunch break, we'll discuss that first, and then once we complete that, we'll move on to we'll discuss the other aspects that we have to consider. So after the lunch break, we'll have one lecture on general aspects of tall building design. And after that, we start looking at the detailed aspects that we have to look into, starting with coupled shear walls. So with that, shall I stop here for lunch?